Go briefly through what we covered in chapter 3 because we are basically finishing this chapter. We finished it actually last time. So this chapter is about half-wave rectifiers, and we have talked about why we call them half-wave because you're effectively using only half of the cycle of your input voltage. So first thing that we covered was a very simple half-wave rectifier. There's only one diode in the system. The diode doesn't need any control or anything, and our load is a very simple load, which is just one single resistor. So we looked at this, we looked at the average value of the output voltage, we looked at, for instance, power factor, parameters like that. Then we thought maybe our load is not as simple as we think it is. Maybe in addition to the resistance, it also has some inductance. So the next we looked at a rectifier which has an RL load, so a resistor placed in series with an inductor. In that case, as we discussed, the current is going to lag the voltage waveform just a little bit. So the conduction of the diode and the polarity of the input voltage do not necessarily overlap with each other. So as you can see over here in the bottom, the sinusoidal waveform is actually our input voltage, and then our current starts as soon as the input voltage tends to get positive, but then the conduction finishes at beta. That's when the inductor current tends to get negative, and therefore the diode has to turn off. Then we did not cover this part in class. This is what appears in the book as well. What if in addition to the resistor and the inductor, we also have a DC source appearing on our load side? For instance, this DC source could be a very large capacitor that has been pre-charged. It could be a battery, or it could be the back EMF of some sort of, for instance, a DC machine. We didn't cover this. Equations are pretty much simple. Again, you see a kind of a delayed conduction for the current, and again, current returns back to zero while the input voltage is in the negative area. Then again, I did not cover this one, and this is what if in addition to the original diode that we have, we also have a freewheeling diode. Over here it is shown as D2, this diode over here, and what happens is you have two diodes. Each diode has two possibilities of being on or off, so totally you have four possibilities. As it turns out, only one of them is the viable possibility. For instance, D1 and D2 cannot be on together at the same time, otherwise we are actually shorting our input voltage source, violating KVL, for instance, so one of these possibilities are out. They cannot be off at the same time, because if you write the voltage equation in this loop, you are going to realize if one of them is off, the other one has to be on, and that's actually the case. So for a case like this, if the input voltage is positive, D1 is conducting. If the input voltage is negative, then D1 immediately turns off, and then D2 conducts. So we are basically having two modes, and the left one is when the input voltage is positive. So you can see actually I'm applying a positive or a growing positive voltage to our RL load, and then as soon as the voltage turns negative, D2 turns on. So basically we have actually like a short circuit applied to the load. Now this is the extra mode that we are observing, and this actually gives us the opportunity for the inductor to continue its current in this loop. So that's called the freewheeling. So basically this current that was already non-zero at the end of this mode is freewheeling through the diode D2 in this mode. And because we are not applying any negative voltages across the output side, we are only applying zero, the inductor current does not drop as quickly as we expect. Therefore, we are going to observe a continuous actually mode of operation for the current of the inductor. So if you actually run this in some sort of like a PSpice or any kind of circuit analysis tool, you are going to realize that your inductor current is actually getting continuous, which is relatively good, because if the current is almost DC, it's not absolutely DC, but it has a basically relatively large DC component, you can argue that the voltage drop across my resistor, if this actually is my output voltage, that is also going to be relatively DC. So actually, if you compare the output voltage waveform, again in this graph, output voltage is defined to be the collective of the voltage across the resistor and the voltage across the inductor. It's either positive or zero, and then the output current is kind of continuous, which is good. Then we spend more time on what if there is a capacitor, or somebody has placed a capacitor in parallel with our resistor. This is to make sure that our output voltage is closer to a DC voltage. And as we discussed last time, there are times that the input voltage tends to get larger than the output voltage, and the diode does not allow that and actually kind of sews them together. And that is actually from, for instance, this time instance, which is marked with 2 pi plus alpha all the way to this point, which could be named as 2 pi plus theta. And then there are time instances that if you look at the equation for the current of the diode, as soon as this current tends to get negative, the diode is not going to support that, therefore the diode is going to turn off. And that happens actually at theta. And after theta, diode is off, so basically what's happening is we have a discharge of and basically a very simple RC circuit. A capacitor is getting discharged through a resistor. So you have an exponential term going back to circuits 1, and that exponential term is actually shown over here. It doesn't really look like exponential because we're only looking at part of it, not the entire curve. And before this capacitor is totally discharged, again in the next cycle, the input voltage, which is this curve over here, which is rising over here, and the output voltage is actually falling. Then as soon as the input voltage tends to get larger than the output, again the diode turns on and kind of clamps them together. So your output voltage is this curve, and then following the sinusoidal input, then this exponential term, and then following the sinusoidal input. So you can see that your output voltage is closer to a DC, and that's actually our ultimate goal in this case. The only problem over here is the conduction of the diodes. This is some simulation result. I would assume it's in PSpice. And as you can see, for instance, here a larger cap has been used, so you almost don't see that exponential behavior, you almost see a straight line. And you can see that the conduction period of the diode is very short, just this little area over here. And plotting the current of the diode, you can see that the current of the diode looks more and more like an impulse of current, which is not necessarily good. The diode is not going to be able to handle that if you do not choose the right diode. So if you look, in this case, for instance, the diode is only conducting here, and then nothing going on for a large portion of time, and then it's conducting over here. So in peak, the diode is actually handling more than 4 amps, but on average, if you take the average value of the signal, it would be somewhere around maybe 0.2 amps. So 20 or maybe 20 times larger than its average value is the peak value of the diode current, which is not a very good thing. So there is a compromise here. If you pick the cap to be very, very large, and for instance, in this case, the cap is relatively large, your output voltage is relatively DC, but your diode is tolerating a lot of stress on its current. But then if you be a little bit relaxed on the selection of the capacitor value and don't pick a very large cap, your output voltage is not very much DC anymore, but again the diode has a larger interval of conduction, which is from 2 pi plus alpha all the way down to 2 pi plus theta. By the way, theta is very close to 90 degrees, maybe 90 degrees and a half, or maybe 91 degrees. Theta is marked over here, so please always check when you're calculating the value of theta, make sure it is not, for instance, 105 degrees. It never happens that theta to be that large. It's very close to 90 degrees, a little bit more than 90 degrees. And alpha, or 2 pi plus alpha, I would say, assuming that alpha is here, alpha is behind 90 degrees, so usually it's around 80 degrees, 75 degrees, depending on what value you choose for your cap, basically. So, and then we moved on to controlled rectifiers. A controlled rectifier is, like in this case, we have replaced our diode with an SCR. The diode makes its own decisions of when to turn on and turn off. But here we have an SCR. At least we can actually command this SCR to turn on whenever we want to, as long as it's in this forward biasing region. So it gives us a little bit of an extra basic degree of freedom, a little bit of control over the system. Like over here, alpha is the triggering angle of the SCR. There is a gate control system, and we adjust it. For instance, there is a knob, or there is a, I don't know, pre-programmed kind of a software program running, and we are asking that whenever the voltage of the input crosses 0 and turns into the positive territories, wait for alpha radians or alpha degrees, in this case it's in radians, and then trigger the gate. So what happens is before that, this SCR is off, so it's actually blocking the voltage. Here is the voltage. And then when we trigger it, it actually turns on because it was in the forward biasing region, and it's turned on, so it behaves like a short circuit over here. And then during the negative area of the input voltage, nothing really happens. Even if you trigger the gate, nothing is going to happen because it's in the reverse blocking region anyway. So if you look at your output voltage is initially 0, and then follows the input voltage, and then becomes 0, and then follows the input voltage. And so basically, if you compare it with the uncontrolled rectifier, you can see that by adjusting the angle of alpha, I can actually carve out a little bit of my output voltage, and that means I have control over the RMS value of this voltage, I have control over the average value of this voltage, you know, things like that. Like here we have this expression of showing the output voltage on average is 1 plus cosine of alpha times Vm over 2 pi. So by adjusting the angle of alpha, we can actually have a variable kind of an output voltage. Then we did not cover this, and this is when you have a controlled rectifier, and in addition to your resistor representing your load, you also have an inductor on the output side. Same story, alpha is the triggering angle for our SCR, so that's when the gate signal comes in, and the SCR, which was previously forward biased, turns on. So this is the voltage drop across the SCR. So now we are actually having input voltage applied to a resistor and an inductor. We have a very simple differential equation to solve, and the current, the solution, which is the current, is actually going to look like this. Tends to get 0 at beta, turns to return back to 0 at beta, and tends to get negative at beta. Then the SCR does not support negative currents similar to a diode, and that's actually when your SCR turns off. So SCR only turns off when its current tends to get negative. So at beta, the SCR turns off, and the rest of the story is the same. You have to wait for the next forward biasing region, again trigger the gate, and basically create something like this. So this is the expression for the waveform that we have for the output current or the loop current, which is basically this curve over here. And then you can actually calculate the average value of the signal and you know, things like that. Again, the book goes on and assumes that there is also some DC source added to the load side, like the back EMF of a DC machine. And again, you have to write the equations and basically solve it, but we didn't actually cover it in class because it's not very common to use these guys like this. One thing that we did not cover, which could be relatively important, is what if our source is not an ideal source and has a little bit of a self-inductance? And that is represented here by this LS, L of the source, the inductance of the source. So this could be assumed that this is the impedance of the line that you are using. If you are using, for instance, power lines, you cannot assume that there is no impedance associated with them and it's just a purely sinusoidal you know, signal, voltage. There is some basically impedance associated with that. So this is actually, you cannot really get rid of this inductance. It's already there. As soon as you plug it in, the impedance of the line appears in your circuit. And then this is assuming that we have both diodes basically. So this is kind of a more realistic version of this circuit. This circuit was an ideal case. There was no impedance or inductance on the load on the source side. But here they are assuming that what if there is some? As it turns out, this inductor you know, creates some extra mode in the system, and that extra mode is there is a time in this particular system that both diodes are going to conduct at the same time. So that's why the term commutation comes in. That means while one of them is turning off, the other one is turning on. It's not instant. Before, if this inductance did not exist, switching from one mode to the other was instantaneous basically. The input voltage was positive, you were here, D1 was conducting, and then as soon as the input voltage tends to get negative, D1 turns on, off, D2 turns on, and you jump basically over here. So you instantly jump from this mode to this mode. Over here, there's a little bit of an overlap between the mode. these two modes. So, and actually that is this little region over here. You can see if you look at the current of diode number 1, this diode over here, initially it's 0, meaning that the diode was off, but the input voltage has got positive. So ideally this diode should turn on instantly, but as you can see, the diode is gradually going up, and D2 should instantly turn off, but because of the existence of this inductance, it is gradually turning off. So in this little time interval, both of the diodes are on basically. And the duration of this time interval is dependent on the value of Ls. If Ls is 0, it's almost 0, instant. If Ls is large, this time is going to last longer. Beyond that, it's basically the classic case of D1 is conducting. Over here, it is assuming that this inductor is very, very large, so output current is almost DC. It's not really DC in most cases, but it is assuming that. D2 is off. So here we have D1 on, D2 off, which is a classic mode that we have seen before, and that is when the output voltage is kind of following a sinusoidal pattern. Then as soon as the input voltage or output voltage returns back to 0, D1 starts turning off and D2 starts turning on. So there is a little bit of an overlap between the conduction of these two diodes over here. We haven't really analyzed, we are not really going to analyze this in detail. Hopefully, if you basically graduate and go into power electronics or industrial electronics business, please remember, if you have line impedance, these simplified modes of operation may not hold. There might be some extra modes of operation in the system. All right, so this was kind of a recap of chapter 3, which we kind of finished last time. And okay, now let's move on to chapter 4. Chapter 4 is actually kind of covering rectifiers again, but this time we are covering full wave rectifiers. And a full wave rectifier is basically a rectifier in which we have at least 4 or 2 diodes or SCRs or devices like that. And as it turns out, we are utilizing our source in the entire cycle. We are not utilizing the source only half of the cycle. So that's why they are called full wave rectifiers. The very first one is, okay, let me go back to my notes. The very first one is, if we have a configuration like this over here, comprised of 4 diodes, it's called a full wave rectifier. And in this case, we are assuming that our load is a very simple load. It's only a purely resistance case. And then later on, we are going to add an inductor, for instance, in series with this load. We are going to add a capacitor in parallel with this load and actually analyze this system in those cases as well. By the way, you may actually look at this topology, which is drawn differently, but please remember they are all the same. And actually, I have drawn all 4 possible cases over here. So technically, this converter or rectifier is exactly the same as this guy, and it is exactly the same as this guy. It's just a matter of how you prefer to draw them. On the very left one, we don't have lines crossing each other. On the other 2, on the right side, we have actually lines crossing each other. This one looks more like a kind of an H. So sometimes they call it a bridge rectifier or an H-bridge rectifier, something like that. So that's where the terminology comes from. All right. So we have an AC source, we have a purely resistive load, and we have 4 diodes. Each diode has 2 possibility of operation. Either it's on, either it's off. So we have 2 times 2 times 2 times 2, 16 viable or potentially viable cases. Obviously, not all of them are going to make sense, and we are going to, for instance, see why. For instance, there's a possibility that all of these, like only D1 is on and the rest of them are off. Okay? So I can assume that this is on, shorted, and the rest of them are off. Okay? I just open them like an open switch. Well, this mode doesn't make sense, because if D1 is on, it should be conducting some current. Then, if it is conducting some current, well, the current cannot go here, and the current cannot go here. So, basically, you can conclude that this is like a contradiction. So this is not a viable mode. So easily you can say D1 cannot be on by itself, only by itself. D2 and D3 and D4 the same. So all of a sudden 4 of these out of 16 modes are out of the picture. Or you can argue that all right, let me clear these a little bit. D1 and D3 cannot be on together. If this guy is on, so I'm just going to replace it with a short circuit, and this guy is also on, like a short circuit as well, then depending on us, let's say our input voltage is positive. So actually you can see that there is some, basically, some positive voltage applied here, and also some positive voltage applied here. That means at least one of these diodes is violating the fact that it is on, but at the same time it is blocking some negative voltages. So that's also not a viable mode. So if you kind of consider all of these 16 modes, there is only one mode that is a viable mode during when the input voltage is positive. So assuming that this is my input voltage, while the input voltage is positive, the only viable mode is D1 and D2 should be on. All right, this is the only mode that does not lead into contradiction. So D1 and D2 are on, and D3 and D4 are off. Okay, so unfortunately I don't have a lot of room here. Let me clean this a little bit. All right. So this is happening when the input voltage is positive. Now when the input voltage is negative, like over here, the only viable mode is D3 and D4 are on. And the other two are off, D1 and D2. So out of those 16 modes, at any given time, one of them is the viable mode, and we have the viable mode depending on the polarity of the input voltage. All right. So if we are in mode 1 and only D1 and D2 are on, so technically what's happening in the system is you're looking at this loop. All right. D1 and D2 are both on. Conduction is going on, and if, for instance, you look at the output voltage waveform, if D1 is on and D2 are on, assuming that these are ideal diodes, they behave more like a short circuit. So technically, output voltage and input voltage are the same. So I'm interested in plotting my output voltage waveform. It's following the waveform of the input voltage. All right. So that's actually mode 1, and in the other mode, what's happening is we are looking at this loop. All right. So D3 and D4 are on. They behave like a short circuit. And if now write a KVL in the loop, you are going to realize that Vout is negative of Vs, or Vs plus Vout should be 0. They are actually opposing each other. So that may, okay, so in this mode, so let me write over here, this would be Vout will be exactly the same as Vn in this mode. And in this mode, we would have Vout is the opposite of Vn. So if Vn is like a negative waveform that I have over here, I have to just multiply it by a negative of 1. So this is going to be my Vn. And I just analyze the system in one period. You just repeat that. All right, so this is going to be your output voltage waveform. If you look at this output voltage, what you are going to realize is at any given time, we have some sort of a non-zero voltage coming from the input applied to the output. So we are utilizing the input voltage the entire time. So this is a full wave rectifier. Okay? So, and obviously you know that these marks are pi radians per second, and this is 2 pi radians per second. Okay, assuming that we are looking at omega t. All right, so quite simple. If the input voltage is positive, D1 and D2 are on, therefore output voltage is the same as the input voltage. And if the input voltage is negative, D3 and D4 are on, and therefore the output voltage is negative, the input voltage. So that's actually, if you do the math, your output voltage is going to be a rectified signal like this. Because our load is a resistive load, the output voltage is, so if somebody asks you about, okay, what about the output current? Well, if you have the output voltage and we are talking about only a resistor, where obviously this is R times I out. So I out is also looking something like this. It's only a scale by a factor of R, dependent on the value of the R. All right. Let's also look at the input voltage. Let's look at the input current waveform. So I'm going to draw the waveform of the input current. Okay, let's pick black this time. Okay, so let me erase this one more time. Okay, so I mean, if this figure that I have copied from the slides, it shows it to be IS, current of the source. I just label it to be IN, the input current. They are basically the same. Okay, so let's go back to the first mode. As I explained, in the first mode, we have D1 and D2 on. So we are applying a positive voltage across the load. So the current is flowing in this direction. So if you follow this current, it's going to be the same current here. It's going to be the same current here. And as you can see, this is in terms of its direction in agreement with the direction that we have assumed for the input current. So in this mode, the input current and the output current are the same. So whatever waveform that I have here as my output current, I'm just going to draw it over here. So this would be, the peak would be Vm over R. Vm is the peak value of the input voltage. So technically Vm is this much. Okay? All right. So as long as we are in the first mode, the load current and the source current are basically the same. Now let's look at the second mode. Okay, in the second mode, what's going on is we have D4 on and then D3 on. All right. So still, we are applying a positive voltage across the load, which is a resistor. So the current is going to flow in this direction. This is the current of our load. So if I just track this current somewhere around here, it's going to be in this direction. It's going to be in this direction as well. So now you can see that the input current is kind of, in terms of its direction, it's the opposite of the load current. So whatever load current that I have, I just have to multiply it by a negative of 1. So if this is my load current, and I just multiply it by a negative of 1, it's going to look like basically this. All right? So as it turns out, my input current is a purely sinusoidal current. All right? And you can also make the argument that the power factor should be 1, basically. Which is very, very good. So ideally, any time that you connect a load to the source, you would like to see a purely sinusoidal current drawn from the source. And this is a good example of that, assuming that the diodes are ideal. And you can achieve a power factor of 1, which is very, very good. Any questions so far? All right, no questions. Okay. So let's look at some other waveforms. For instance, what is the voltage drop? So let's say you're answering to a quiz question, and you have been asked to sketch the voltage waveform across one of the diodes. For instance, I don't know, VD1, for instance. Remember, when it comes to a diode, you always make the basically polarity from anode to cathode. And as it turns out, VD1 is the same as VD2. Okay, assuming the diodes are ideal and identical. Okay? So let's take a look at that. We just argued that in the first mode, these two diodes are on. So if I'm interested in plotting their waveform, if they are on, they are basically exhibiting 0. So, all right, let me, okay. So we are looking at VD1, which is the same as VD2. In the first mode, both of these diodes are on, so 0. All right. Now let's look at the second mode. In the second mode, we have a short circuit here. Okay? And V out is the negative of Vn. So basically, V out is the negative of Vn. So if you apply KVL to this triangle, you're going to realize that VD1 is the same as the input voltage. So whatever waveform I have for the input voltage, I should plot it over here. So input voltage is negative, so I'm just going to follow that negative trend. All right. Then again, the next cycle starts. VD1 and VD2 turn on, so they are exhibiting something like this. All right. So here, this is basically VD1 is the same as VD2, and they are both equal to Vn. Okay? Or negative V out, basically. All right. And please, whenever you plot the voltage drop across a diode, when you're done, take a look and make sure it makes sense. When you're plotting the voltage drop across a diode, it should always be either 0 or negative. It should never be positive. And as you can see here, it's either 0 or negative, so therefore it makes sense. Then somebody may ask you, okay, what is the waveform for the current of these two diodes? So let me actually see if I have room over here to add that one. Yeah, we have a little bit of room. Hold on. All right. All right. I'm trying to delete this, which I don't think that's going to, okay, it's going to jump up. Okay. All right. Now let's look at the current waveform of these two diodes. Okay. So remember, these two diodes are off in the second mode. So, okay, so let's go back. First of all, highlight what's happening here. Let me just erase a bunch of stuff. So here we are looking at ID1, which happens to be the same as ID2. And again, please remember, when it comes to discussing the current of a diode, it is always, the assumption is it's flowing from anode to cathode. Okay. So in the first mode, these two diodes are on. In the second mode, they are off. So the second mode is easy. I already know that in the second mode, these two diodes are off. So there is no current passing through them. So 0. Okay. What about the first mode? In the first mode, I mean, looking at this loop, the current of the diode and the current of the load, and also the current of the source, they are all the same. So if this is the current of my load, I just have to draw that. Oops, sorry, in the first mode, not the second mode. This guy over here. So that's what I'm going to do. I'm just going to plot this. So the peak would be Vm over R. Okay? So we discussed two of the diodes. You can figure out what the waveform in terms of voltage and current of the other two diodes actually look like. And again, when you're plotting the current waveform of a diode, when you're done, please re-examine your work. Make sure it's either always positive or 0. And that's actually the case for our waveform that we just plotted. It's either positive or 0. It never gets negative. All right, any questions? All right. So as you can see, a full wave rectifier gives us the opportunity to better utilize our source in the entire period, not just half of the period. And once you figure out all these waveforms, what you got to do is you got to, for instance, find out what is the average value of the output voltage, what is the RMS value of the output voltage. And we just argued that power factor is 1 anyway. What is the RMS value of the input current, you know, those kind of things. So what I have here on the second, by the way, I had one page of my slides, my handwritten notes, that basically I'm kind of plotting the same waveforms and the same operating modes. And now let's take a look at these equations. All right. If you look at this basically system, as it turns out, this system is kind of giving you the absolute value of the input signal. So if you want to describe your output voltage, you can argue that the output voltage is the absolute value of the input voltage. So if you want to model this in, for instance, Simulink, and you don't want to get into the details of the diodes and things like that, you can just use an absolute block, and that's actually your full wave rectifier. Then the next question is, okay, what is the average value of the output voltage? So there is a, hold on, there is an average signal symbol missing here. What is the average value of the output voltage? In this case, you can look at the waveform of the output voltage, which was this guy over here, and identify its period, and then take the average. As it turns out, over here, my period is pi. But it doesn't really hurt if you do the averaging over 2 pi, but again, different nodes may reflect different actually boundaries for your integration. Over here, let's say I was not aware of the fact, and I was actually doing the integration over 2 pi. So 1 over the period that I have identified, which is 2 pi, times the integration over 2 pi of this absolute value of the signal, which would be equivalent of doing this integration over 1/2 of the cycle. So basically here you would say this would be equivalent to and please remember, if you are basically using pi as the end of your, for instance, 2 pi as the end of your period, that means your time axis is in omega t. So always you have to use d omega t. Do not use dt, because all of a sudden your numbers are going to be very, very small. All right. So if you do the integration, you are going to realize that your output voltage on average is twice the peak value of the input voltage divided by pi. If you compare that with the half wave rectifier, we had that expression for a half wave rectifier. Oops. Okay, so this was for a half wave. So you can argue that all of a sudden the average value of your output voltage is twice for a full wave rectifier compared to a half wave rectifier. What about the average value of the output current? In this case, our load is just a resistor, so voltage, output voltage and output current are proportional with each other. So if I have the average value of the output voltage, I have to just divide that by the value of R to get the output voltage, the average value of the output current, and that actually this is shown over here. So on average, my load current is twice the peak value of the input voltage over pi over the value of the load resistance. Okay. What about the RMS value of the output voltage? Again, you have to identify the boundaries and always go with the original definition for the RMS value of a signal. So this is actually shown over here. So I'm looking at the square root of the average value of my signal if my signal is actually multiplied by itself. So my original signal was the absolute value of the Vn multiplied by itself. So I have a power of 2 over here. And then integration over 1 period of this thing. This could also be written in this way. Let me just write it over here. Because my system has like twice the line frequency symmetry, I can say this would be also equal to oops. So these would be the same. Either do the integration over 1/2 of the cycle or the entire period, because as you can see, our waveform, I mean, if you see the symmetry is actually repeating itself over pi, not necessarily 2 pi, but it doesn't hurt using pi or 2 pi. Either way would be fine. All right. If you do the math, this turns out to be Vm over the square root of 2. All right. So the RMS value of the output voltage is the peak value of the input voltage over the square root of 2. And that makes sense, because if you fully rectify a signal, its RMS value should not change. So if my input voltage was this signal, on RMS value would be Vm over the square root of 2. Okay, the RMS value of a sinusoidal signal. And if I fully rectify it, the RMS value doesn't change. The only difference between these two signals is the polarity of them in the second half. And if you multiply it by itself, that polarity doesn't matter. Therefore, the RMS value of these two signals are the same. What about the RMS value of the output current? Again, load is a resistive, purely resistive load. Then you just find the RMS value of the output voltage that we just found, then divided by R. That's the RMS value of your output current. And what about the power factor? Earlier when I was plotting this waveform, power factor turns out to be 1. But if you really want to write the equations and figure it out for yourself, power factor was defined to be the ratio between the average output power and the, for instance, apparent input power, something like that, or average input power divided by apparent input power. And it doesn't matter if you look at the average value of the output power or the input power, they are all the same, because we are assuming the diodes are ideal. And that would be, for instance, our output power would be the value of the load times RMS value of its current squared. Or you could write it in this way. This would be, again, the same as the RMS value of the output voltage squared over R. And that's why we were finding these RMS values, because using those we can actually find the output power, average value of the output power. And in terms of apparent power, my input current and input voltage, they are both sinusoidal signals. So all I have to do is find their RMS values and multiply them by each other. This is the RMS value of my input voltage. Peak value is Vm, therefore Vm over the square root of 2 is the average, is the RMS value. And this is the input current. And anyway, if you do the math, all of these parameters are going to cancel out each other, and your power factor would be an ideal case of just 1, which is very, very good. All right. Any questions? And by the way, later on we have a table kind of comparing all of these rectifiers versus each other in terms of, for instance, power factor, I don't know, average value, those kind of things. All right. So as you saw, we used 4 diodes instead of the previous case of only using 1 diode for a half-wave rectifier. Here we use 4 diodes, and this gave us better conditions in terms of we are fully utilizing the input voltage. Our power factor is 1. On average, our DC value on the output side is twice of what it was before. So things are actually much better. Although you may argue that, okay, we are basically using 4 diodes, it is going to cost us a little bit more, and also the reliability of 4 diodes is worse than the reliability of only 1 diode. So if, for instance, 1 out of these 4 diodes fails, the whole system is going to fail, so, or at least it's going to turn into a half-wave rectifier. But so these are the disadvantages. Now, one other way of doing so is called a center tap transformer rectifier. Okay, C is missing over here. As you can see in the schematic of this rectifier, we are only going to use 2 diodes, so we are kind of saving a little of money, and also reliability is going to get a little bit better. But instead, we are using a transformer. Here it is. And the primary side of this transformer is just regular. There's no tapped in it, but On the secondary side, it is center tap, meaning that if you look at the secondary side, for instance, if the secondary side has 200 turns, we have 100 turns over here, then another 100 turns over here, then we have taken a kind of a terminal in the middle of it, so it's called a center tap, basically, transformer. Okay. As it turns out, this rectifier over here is exactly the same as what we just analyzed. However, it only uses 2 diodes, which is relatively good. But at the same time, you also need to have a transformer. Although you may argue that I'm going to use a transformer anyway in the system to provide some sort of an isolation from my primary side to the secondary side. So you may argue that even in a topology like this, if I want to comply with some standards, I really have to have a transformer here anyway. So using a transformer is not necessarily bad, because sometimes you really have to do it because that's the standard. You have to comply with the standard. Doesn't matter if you're using a full bridge rectifier or a half bridge rectifier. Although you may argue that here we need to have access to the central point of the windings on the secondary side, and what if it is not exactly the center of the, a number of turns, there might be a little bit of an asymmetry introduced into the system. But anyway, let's analyze this one this time. All right, so here is our schematic. We have one transformer. The secondary side of this transformer, we have access to the central point of the transformer, and then we have 2 diodes of D1 and D2 and our purely resistive load of R. Okay, so let me see if I can copy and paste a bunch of stuff here. All right. So let's go back here and just copy this thing. All right, need a little bit of more room. Okay. So now again we have 2 diodes. Each diode has a possibility of conducting or not conducting, so we are looking at a total of 4 possibilities. So I'm assuming that now we are getting better and faster at this, so we are not really going to do that analysis. Somebody has done it before. The analysis turns out to conclude like, if the input voltage is positive, D1 is the one that is conducting, and if the input voltage is negative, D2 is the one that is conducting, and there is no other possibility that is viable. So the rest of them are going to lead to some sort of a contradiction. So if this is my input voltage, you can argue that when the input voltage is positive, like in this area, D1 is on, and the other one is off, basically. And when the input voltage is negative, which is in this area, D2 is on. And D1 is off, basically. So when we don't mention the status of a diode, the assumption is off, basically. All right. So let's take a look at this one. First thing that you have to note is that, I don't know, in my notes, instead of VS1, I am just labeling to be VN1. So instead of source, I'm using IN, which is actually the input kind of waveform, but doesn't matter. So I can actually argue that, going back to how an ideal transformer operates, you can say VS1 is the same as VS2. Why is that? Because the number of turns on the top part of the primary side is exactly the same as the number of turns on the bottom side of the primary side. And they are both equal to proportional with the input voltage, because this is a transformer multiplied by the number of, some sort of a number of turns. In this case, something like this. Okay. So where is this coming from? It depends on what or how N2 is defined. is N2 the number of, I had this, okay. If N2, okay, let me redraw this one more time here. On the primary side, there is no ambiguity. I already know how many turns I have, N1. Now, on the secondary side, it depends on how you count them. Count them, basically. You would say, is this N2 and this is another N2 turns, or this is half of my turns, total turns on the secondary side, and the bottom one is also half of the total turns. So depending on how you determine or define N2, your equations may be different. The note that I have over here, the 2 that appears here is actually in agreement with this guy over here. However, if you open another book and you realize they're assuming that we have N2 turns over here and N2 turns also over here, then there shouldn't be a division by 2 over here. So it's actually the matter of the convenience of the author of the book. Here, I think in this book, the assumption is these all exist. Okay? So N2 is the total number of turns on the secondary side, not half of it. All right. So we have an ideal transformer, and this equation over here holds for this ideal transformer. Okay? Now, assuming that this equation holds, I can argue that I have 2 modes of operation. That is, one of them is when the input voltage is positive. The other one is when the input voltage is negative. And when the input voltage is positive, D1 conducts, and otherwise D2 conducts. So looking at the modes, I actually have the modes drawn in my notes. Let me just go through them. So, or maybe I can just plot them here. In the first mode, D1 is on, so basically you have action going on here in this loop. And D2 is off, so we don't really care what's going on in the bottom loop. So this is mode 1. In the second mode, there's action going on in this bottom loop. And nothing is happening on the top loop because D1 is off. So let's look at the first mode. So in the first mode, D1 is on, so this is the loop that is active. And as it turns out, if you apply KVL to this loop, you're going to realize in this mode, V out is the same as VS1. And VS1, according to this equation, was proportional with the input voltage. So if my input voltage is drawn up here, my output voltage is going to be like this. Just proportional with that, okay? So to show this proportionality, first of all, this is my output voltage. If peak value of the input voltage was Vm, over here this Vm would be Vm times N2 over 2N1. So we are just showing that this is proportional with the input voltage. So this is mode 1. And this mode is basically lasting or starting at omega t equals to 0 all the way down to omega t equals to pi. All right. Now what about the second mode? So let's look at the second mode. In the second mode, we have this loop in action. D2 is on, and if you apply KVL over here in this mode, you are going to realize that V out is negative of VS2. All right? So whatever VS2 is, I have to multiply it by a negative of 1 and draw it over here. VS2 is proportional with the input voltage, so I have to multiply it by negative 1. And the input voltage, you can see it's negative. So if I multiply it by another negative, it's going to be positive. All right? And again, it's all in proportion with each other. So again, peak is Vm times N2 over 2N1. And that's the end of my cycle. And this thing just continues. So you can see again, you got a full wave kind of a rectification action that was going on in the previous case that we were using 4 diodes. The same thing is actually happening over here. And please remember, again, our load is a purely resistive load. So if I'm discussing V out, I'm also discussing I out because they are proportional with each other. And let's say you're curious about, for instance, what is the voltage waveform. Again, if you, for instance, study the input current, it's going to be similar to the previous case. It's a purely sinusoidal case, that therefore your power factor is 1, for instance. So I'm not going to plot that. But let's look at the voltage drop across D1. Let's say we are curious about what the voltage waveform looks like. So let me use black color maybe. So let's say I'm trying to purchase this diode. The first thing that you are going to question yourself is, okay, how much voltage this diode has to block when it is off. So that's why we are looking at the voltage drop across this diode. So let me erase this. All right. So I already discussed that in the first mode, this diode is on. So there is no voltage drop on the diode. It's an ideal diode. Okay, so 0. No problem so far. Now let's look at the second mode. Okay, second mode, this diode is on. So I'm just going to replace it, with a short circuit. All right, and we already know whenever it comes to a diode, we always assume that the voltage is measured from anode with respect to its cathode. So we are actually looking at this diode voltage. So all you have to do is actually write KVL in this loop. All right. So we have two diodes and the secondary side of the transformer. If you write the equation, you are going to realize that the equation is like this. Let me just write it over here. VD1 turns out to be VS1 plus VS2. And VS1 and VS2 are identical, so it's like twice VS1 or twice VS2. And VS1 is already shown over here, so I just plug in those equations. So this is going to be Vn times N2 over N1. Okay, so it's just a factor of N2 over N1 happening over here. All right, so if I plot it, it's just proportional with the input voltage with a scaling factor of N2 over N1. So it's going to look like this. So if you are curious about this peak value, this would be whenever my input voltage is at its negative peak value, which is Vm with a negative sign times N2 over N1. Okay. All right, am I missing something here? Hold on. Yeah. Is it? There's a factor of 2 missing somewhere.
Yeah, N2 over 2.
N2 over 2. Oh no, we've multiplied that by this 2 over here. So that 2 cancels out this 2. Okay, so this is actually how it looks like. Okay. Any questions so far? So actually, if you compare this with the maximum value of your output voltage, so remember, this was the maximum value of the output voltage. The diodes are handling twice as much of that output voltage. So please remember, the peak negative voltage that appears across your diodes when they are off is twice the maximum value of the output voltage. Let me actually write it over here. I don't think we need this. Let me just delete this. Okay, so I'm just going to write it over here. I don't know whether I should call it VD max or VD min, because when you want to purchase the diode, you don't talk about the polarity of the signal. You just talk about how large it is. This would be twice the peak value of your input voltage. So basically what I'm saying is this height is twice as much of this height. Okay? So on peak, if your output voltage is supposed to be 100 volts, you should buy a diode that can tolerate 200 volts, something like that. All right. Any questions? All right. So I guess I'm going to stop here. We are going to have our first quiz. So I'm just going to let me write a note over here. It's quiz number 1. As I asked you guys, please, when you're done, just sit, and I'm going to collect all of the sheets together. It's only 1 page. If you need extra sheet, raise your hand. I have some extra sheets over here you could use, but hopefully those are not going to be needed. So I'm going to start from, so you just go back all the way.